In this video, we are going to attempt to solve this system of equations and where x and y are functions of t and the derivatives are functions of x and y only. So you can rewrite them like this as before. Okay, so that is we got this here. Now we can change it to matrix form in the following manner. That is, just go ahead, take a 2 by 1 matrix with x prime and y prime in the column, and then we'll form a coefficient matrix, okay, depending on the coefficients here, and then we would have x, y. So how have we been dealing with such questions? What we do first is that we would like to find the eigenvalues of this matrix, which we call the coefficient matrix. And we saw the cases where the eigenvalues were real and different. And then we saw a case where the eigenvalues were same and real, of course. So now we are going to see what happens in this case where eigenvalue is actually going to be imaginary. And again, just recalling the procedure that if, or in other words, if lambda is an eigenvalue, all right, so if lambda is an eigenvalue, what does that imply is that this determinant that we obtain by subtracting lambda from the diagonal elements, okay, that determinant has to be 0. So what do we get here simply is that this determinant is 0, which means that 1 minus lambda is square, right? Plus, and then minus negative 1 times positive 1. Sorry about the typo. Okay. So negative 1 times positive 1. So this will be 0, which means that if we FOIL this, what will we get is lambda is square minus 2 lambda plus 1. So we get lambda square plus, or sorry, minus 2 lambda, okay, plus 1, and then here this becomes plus 1 equals 0, which gives us lambda square minus 2 lambda plus 2 equals 0, right? Now, you know it can't factor, so we are going to use the quadratic formula. So if we use the quadratic formula, then what will happen is we are going to get negative of negative 2 is 2, then we get a plus minus sign, and then we get a square root, and then we get negative 2, then quantity square minus 4 times 1 times what? 2 divided by, coefficient here is 1, so divided by 2. So what we get then is that this whole thing equals how much? 2 plus minus, here we get 4 minus 8, that is the square root of negative 4 divided by 2. So what the eigenvalues are then? The eigenvalues are, let's just first go ahead and abbreviate it further. That is, see, if we factor a 4 out, then this will become a 2, right? And you all know that square root of negative 1 That's the complex number I, right? And if we factor a 2 out, we will get 1 plus minus I as our eigenvalues. So now let's go ahead and find an eigenvector corresponding to 1 plus I, say. We could have done 1 minus I as well. So here, remember this, the way we work on this is this. That is, if we take an eigenvector, say uv of this, sorry about that, of this eigenvalue, then what has to happen is this, that if we multiply this matrix with uv, or the column vector uv, we should get 0, 0, right? Okay. And here, of course, our lambda is how much? 1 plus I. So let's go ahead and write it in. Okay. So that's what we have. And then if we go ahead further working with this, what we get is the following. That is, we get negative I, then 1, and then negative 1, and then negative I as well, right? Okay, so that becomes 0, 0. So what this implies is that you will get two equations as a consequence of this. One of them is negative IU plus V equals 0. The other one is negative V minus, sorry, negative U minus IV equals 0. So first one gives, what does the first one give? The first one will give V is IU, and here you will get, U as negative IV. All right. So if we look at this vector UV according to the first equation, okay, so say we are taking the first equation and we got UV, so according to this relationship, what this becomes is U, then IU on the bottom. I can factor U out. Okay, so what will that leave behind? 1i. So all the eigenvectors are multiple of 1i. Now say we go according to this one. Say u equals iv. All right. And then, so what will this tell us? This tells us that now instead of having this, we can write u in terms of v. So we got this here. We got a v on the bottom. So this is v times what? Negative I, 1. But notice this, that this vector and this vector are just multiples of each other. Why? Because look at this here. If you take this, multiply this vector, say, by I, right? Then what do you get? You get I square, okay? All right, rather negative I square on the top and I on the bottom. Negative I square is 1. So what do you get? You get 1i again, right? So we are getting a complex multiple of the same vector, okay, or same eigenvector actually. So our strategy here is going to be this. we have complex numbers, but we are going to stay in the realm of real valued solutions. So what we would do is this. First, recall that this is an eigenvector corresponding to the eigenvalue 1 plus I. So a solution is going to be, remember what we did? We took E, we raised the power, okay? We raised the power what? Just the, whatever the eigen value is, and we multiplied that with eigenvector. So let's take this eigenvector. I mean, I can take either of the two, and we will arrive at the same conclusion. So what our strategy is going to be is this. That is, we will expand this and extract the real and complex part of this, or separate them, okay? And then what will happen is this, that if they turn out to be linearly independent, then that will give us two linearly independent solutions. And if you work with any other solution that you obtain as an eigenvector, you will see you find the same solution. By the way, here 1 times t should be a t. Now, so we have e to the t, okay, and then e to the it. Remember this by very famous Euler's formula is what? Simply cosine t plus I sine t, and then we got all that multiplied by this vector, right? Okay, so let's just do a little bit algebra, not too much. It should be over pretty soon. Okay, and so we got this here, and I'm just going to do, since I've written it already here, I'm just going to multiply these out. So here 1 times this is this vector, and then we have I times the same quantity. And so if we go ahead and write them separately, then what do we get? We get this I cosine t, and then what here? I square sine t, right? And let's not have the parentheses here. So now what happens is this, and remember this, as I told you, it's guaranteed that no matter which vector you start with, you'll get to the same conclusion, okay? So this becomes what then? This will become, the I square will simply become -1, so that just becomes negative sine t. I'm just rewriting it. That is, I'm just going to put this first, just as a tradition, because it's the real part. And then what happens is that the solution may be written as, I can just go ahead and split the real and imaginary part. So what is the real part? The real part is this, that is cosine t, and then negative sine t, and the imaginary part is plus I, then again e to the t, and this time it just changes to, if you look at this here, it changes to sine t cosine t, right? Sine t cosine t. So you can just go ahead and verify that these two, first of all, you may notice that, look at this here and look at this here. These two vectors are linearly independent, so their scalar multiples will be linearly independent as well, all right, by the same quantity. So these are linearly independent solutions of the system, okay? And as I said, even if you work with the other eigenvalue or the other eigenvector, you will get to the same conclusion, means you'll get to an equivalent result. So what happens here is that we got two linearly independent solutions. So we can write the final solution as x, y equals c sub 1, okay, the first vector, all right, then plus c sub 2 times e to the t, okay, and then the other vector, all right. So now you can see that here, I mean, we have these exponentials here, and they are multiplied with these trig functions. So let's go ahead and see how their, how their slope field looks like, or vector field looks like, and how does their phase plane looks like, okay, look like, I'm sorry. All right. Now, before we go towards the vector field, let's just look at just very basic graphic nature of these solutions. So say if I multiply these in and combine them together, what will happen is that the solution would be, this will be the x value of the x function, this is y function, and if we plot xy into xy plane for various values of t, we will get a parametric curve. So let's see how does that parametric curve looks like, or will look like in various situations. So we will take a very basic situation. Say we are taking C1 equals 1 and C2 equals 0. So what will happen in that case is that this guy xy, this is going to become, I mean, this vector, I should say, C1 is 1, so we got e to the t cosine t, and here we will get negative e to the t sine t, right? So, and you can graph this, parametric curve by using your graphing calculator or Desmos or GeoGebra. You have seen all those. So I'm just graphing it, just using this program called Scientific Workplace that I am creating this video by using. So here we go. So if I graph it, you can see e to the t is going to make it, really large because it will grow exponentially, and sine and cosine are going to pull it back. So, as you see this here, you know, the values increase, and sine and cosine will be pulling it, back towards, I don't know how to put that in words, but don't worry. Let's just go ahead and see for ourselves. For instance, let's see if we just go from 0 to 2 pi, all right, then how would the graph look like? So see, from 0 to 2 pi, starts at 1, 0, and then comes back here at 500 some, and then 0. Or if we go from, say, 0 to 4 pi approximately, all right, then again it starts at 1, 0 and goes down here, okay, because I went slightly more than 2 pi. Or say we go from 2 pi to approximately 4 pi, all right, then you can see it's starting here at 500 some and ending up here. So let's just go ahead and see how do the computer generated solution on that slope field plotter of Dr. Nestor's website, how do they look like? Okay, so here we are at the slope field plotter of Dr. Nestor, and I have put the this URL in the video description. So what we have here is x plus y and then negative x plus y, right? Okay, let's keep these guys here 4 to 4 as much as, you know. Okay, so you can see this here that we have spirals emerging from the origin. And why is that happening? It's happening because of the e to the t part. All right. So, and since our we have e to the positive t, that's why you can see they are all spiraling outwards from the origin. Okay, or you can call this origin a spiral source. And if you look at all the solutions here, what you have is that, you can see they just spiral out, and you could see that they're going to be much more than from negative 4 to 4, because of the way e to the t is going to behave. And here are the x, and on below you can see the graphs of xt and yt, how those values change. Okay, so what we notice here, that when we have uh, e to a positive power of t, all right, then in that case, we have this, that we have these solutions are spiraling out. And in this particular case, you can see that they are going clockwise around the origin. They may go counterclockwise as well. Let me show you an example. So say we are looking at this system and we go ahead. Now we are not going to, go ahead and calculate the eigenvalues and eigenvectors by hand. We'll just let this package compute it. All right. So what you have is here, this 2 is going to give you e to a positive power on t, right? And let's see what happens when we go to our slope plotter. So what we have here is negative x plus 5, minus 5y. Yeah, I have the equation open in another window. And well, in this one, I shall show a situation when that happens. All right, or we will see how the eigenvectors here look like. And then we got 3x plus 5y. So now you can see this here, we had e to the positive, e to the 2t, right? And here what's happening is, again, this will be a spiral source. Solutions will be spiraling. And here they are spiraling what? Counterclockwise from the origin. Okay, now let's see a couple of more examples, how their behavior are, then I'll just let you play with it on your own. Okay, now say we are looking at this system of equations. Now let's go ahead and have the computer calculate the eigenvalues and eigenvectors. So here you can see we got negative 2. So now we will have e to the negative 2t and then linear combinations of sine and cosine. And that negative 2t would do what? That will let them spiral inwards. So let's go to the slope field plotter and see. So what we have here is we are changing these to positive and making these what? Negative, right? And now you can see that they are all spiraling inwards, and in this case it's going clockwise. They are spiraling in, and the solutions are going like clockwise towards the origin. Okay, now let's take one more example and then stop. All right, so we have this coefficient matrix. So let's look for the eigenvalues and eigenvectors, and rather corresponding eigenvectors. So here we go. So in this case, what we see is that the These are the eigenvalues. So what is the real part here? The real part here is 0. So that means what will be a part of our solution? That will be e to the power 0t. That means that there is not going to be any exponential portion in the solution, because this will be e to the power 0, that is 1, and everything is going to depend on sine and cosine. So let's see how do the solutions of this look like. So here we are again at the slope field plotter, and what we got here is x plus y, and on the bottom we have negative 2x minus y. And now what we see is we don't have a spiral, we just have the solutions. Just, as you increase the values of t or change the constants c1 and c2, they just circle around according to the behavior of sine t and cosine t. And in this case, the solutions are going, as you can see, clockwise around the origin, and here you call origin the center. Okay, so just play with more examples and we will see what happens when we bring non-linear portion into it. Okay,